My name is Justin, and today I'm going to be talking about robotics. Just a brief overview of what I'm going to be talking about today. First, we're going to talk about what is a robot and what's not a robot, how robots work, some engineering principles, and we'll talk a little bit about some math behind the robots and a little bit of physics too. And then we'll talk about competitive robotics, which is something that I have a lot of experience with personally. And then we'll finish off with some examples of robotics in the world today and in the future. And feel free to ask questions at any time throughout the talk. I think Justin Sun will be handling those. So first, let's talk about what a robot is. A robot has a lot of definitions, and it's hard to pin it necessarily on one thing. I've pulled up a few definitions just from various dictionaries here. Oftentimes they'll mention motion and control as the two biggest things that quantify a robot. The robot has to be able to move, and the robot has to be able to make decisions and control its actions. So let's look a little bit more about what that means. So we're going to start off with a little game that I like to call Robot or Not. Very clever. So here's our first example here. This is something that is built by Honda. It's called the Osmo. It's based off Isaac Asimov, who's one of the founding minds behind the principle of robotics. But who thinks that this is a robot? This is in fact a robot. This is a pretty clear example of a robot. It looks like you'd see robots in movies. It functions autonomously. It can walk around. It can make independent decisions. It steers itself. It responds to environmental features. It can talk to people. This is a pretty cut and dry example of a robot. But let's talk about something a little bit harder, maybe. What about this? You have a car. Is a car a robot? I'll give you a second to think about it. It is, in fact, a robot. And if you look at the two criteria for being a robot, it moves as clearly because it's a car. But the more interesting thing to think about is that it does perform functions on its own with control. That's not to say that a robot can't be controlled by humans, and many robots are controlled by humans, but a car does a lot of things autonomously. That means without human control that you don't really think about. For instance, how fast to rev the engine, how much fuel to mix with oxygen, how fast to spin the fans in the air conditioning. And some cars even have more advanced features like automatic corrective steering, GPS navigation, blind spot monitoring. Those are all things that the car does on its own because somebody programmed it to do that, somebody built it to do that, somebody set it up so that it does that. And it does it on its own without you needing to tell it, hey, do this for me, do that for me. It does it on its own. So that's another example of a robot that you might not think, it doesn't look like a robot you see in movies, doesn't look like the Osmo, but it is in fact a robot. And so now let's take a look at one last example here. Here's an iPhone. I'm sure most of you, if not all of you, have seen an iPhone or some sort of smartphone. Is an iPhone a robot? Why don't you put your answer in the chat? And remember that it has to meet those two characteristics of thinking for itself and moving. Oh, here we go. There seems to be a kind of split answer on here where some people are saying yes and some people are saying no. And it looks like the thing that people have called into question here is the fact that it doesn't move. And so clearly a iPhone can think for itself. It has a bunch of automatic processes. It pops up notifications. It opens the app that you tell it to open. It has timers, incoming calls, all sorts of these things. So clearly it satisfies that condition, but does it move? And your gut instinct might be no, that it doesn't move because it's a phone and it sits there until you pick it up. But actually, this is hard to tell from looking at it. But when a phone vibrates, the way that it vibrates is actually a small motor inside the phone with a little piece of metal on it, and that's what causes it to vibrate. And so that motor spinning makes it a robot. If it didn't have that motor, I'd say it's not a robot. But because it has that motor, it's a robot. So we've talked about what is and isn't a robot, but let's take a look a little bit more about what makes up a robot. Every robot has these three things in it. Usually there'll be more things attached to it, but at its core, every single robot has a power source, a motor, and some sort of control circuitry. The best way that I like to think about these is like the parts of the human body. The power source is kind of like your heart. It pumps energy to the rest of the robot, just like your heart pumps blood to your body, and it supplies the power that the robot needs to run. The motor is kind of like your arms or your legs, and it takes the power from the battery and it turns that into mechanical motion. And that's how you can do things like spin the wheels on a car or vibrate your phone, or operate a robotic arm. And finally, the control circuitry is most analogous to your brain. It tells the robot what to do, when to do it, and how to do it. And that's where decisions are made in the robot. And those are often done both by hardware through different components on the circuit, or by software through code and through logic. And so that's an overview of the three components, but let's take a look at them more specifically. So these are all motors. Motors come in many different shapes and sizes. This isn't all the types here, but these are some of the most common. And they have lots of different purposes and uses, and each different type has its own cases where you use it, or sometimes you'd use a different type. The first type here is the DC motor. This is a powerful motor, more powerful than some of the other things. It's often used for things that require a lot of force because it can provide that power. Whereas something like a servo motor is less for power and more for precision, because you can control it much more accurately than a DC motor. Servos have a limitation that most of them can only rotate 180 degrees, whereas a DC motor can spin forever. Servo motors hit a limit once they get to 180 degrees, and then they have to go back. But sometimes that can be an advantage if you only want a motor to be able to turn that far, or if you want to have the precision of being able to go back and forth, because a DC motor doesn't have as much precision and it's harder to get it to go back and forth as precisely. And another type of motor here is the stepper motor. That's a very complex type of motor. Rather than just power like a DC motor, it takes in a kind of interesting waveform signal, which means that the signal has information in it, and that information gives it very precise control. And the reason why is because it's in the name. Actually, it's a stepper motor because it makes little steps towards the direction it wants, rather than something like a DC motor, which is just a continuously rotating thing. And that gives you a lot of precision, but what you trade off for the precision is it's a little less powerful, and it's slower compared to some of the other motors. So let's take a look inside a motor. This is quite an interesting thing. This is a DC motor, what it looks like on the inside. It looks pretty complex, but it's actually one of the simplest motors there is. And so what you're seeing here is you're seeing three of what are called electromagnets. And electromagnets are very, very cool, and they've all sorts of different applications. But what they're used for here is, you see the little red coils with the arrows on them? Those are the electromagnets, and they have a coil of wire. And when you run electricity through a coil of wire, something very interesting happens, and it makes a temporary magnet. And so these north and south here, these are permanent magnets, kind of like, you'd have on your fridge. But these, as you can see, the little slivers hanging off here, those are showing what polarity the magnet has. And if that's the positive, or so the north, then it'll be in red. And if it's south, then it'll be in blue. And so that magnets, if you put a north next to a north, it's going to repel. And so you can see, as it comes over here, it puts a north next to the north. And that's because the direction of current, which is the flow of electrons, kind of represented by this arrow here, is making the electromagnet in such a way that it pushes off of this north part here and gets attracted to the south part over here. And then you can see, once it reaches the south part, it changes back to south, and it suddenly repels from the south part over here and attracts to the north over there. And that continuous pattern is what makes this spinning motion of a motor that you see. And there are much more complicated kinds. There are motors that use hundreds of electromagnets. There are motors that use very different designs, but this kind of gives you an idea of how a motor really works and how you turn electricity into that mechanical motion. It's great to know where the motor is, but as you kind of see in this diagram, that there's this power that comes in from somewhere and it goes out to somewhere. But where does that power come from? And so to figure that out, we have to look at power sources. And so every robot, as we talked about, has a power source. Power sources can be lots of different things. It could be a battery, it could be a generator, it could be a solar panel. The engine of a car is a power source. A turbine, a water wheel, or any number of things really can be a power source. Power sources work by creating something called a potential difference, where the electric potential at one end is different than the electric potential at the other end. And that potential difference causes something called a current. And a current is basically a flow of electrons. So electrons are what carry charge in an electrical circuit. The electrons are what actually bring power from one area of the circuit to the other area of the robot. And so this potential difference creates a current through the robot. Can I hear? Do you have a question? Is that?
Do robots necessarily need a control?
Yes, and that's not to say that everything that's mechanical has an electrical circuit in it needs control, but to be a robot and to have, you remember we talked earlier about the two
Yeah.
conditions of being a robot, that it has to move and then it has to be able to make independent decisions. That's where the second part of that comes in. So the control circuitry is where those decisions are made. And the control can be very basic, or it can be really advanced in the case of some robots, but it always needs to be there in order for it to qualify as a robot. Now, you can have mechanical machines that don't have that. You can plug a motor directly into a battery and it'll spin, but that doesn't qualify as a robot because it has the motion, but it doesn't have the control. Why is the generator so big? The generator is so big for a few reasons. One is that the source of power is different than some of the other things. For instance, in a battery, the source of power is a chemical reaction inside the battery, where you have certain chemicals that undergo a reaction and they provide that potential difference. A generator, as you can see, has this big yellow thing on the top. That's usually for gasoline or for diesel, and that takes up a lot of room. And also the generator provides a lot more power than something like a battery, and that's usually why it's bigger. You can have different sizes of generators. There are generators that power whole buildings. There are generators that just power a bike pump, and depending on the use or the needs. The generator can be different sizes. It also the reaction of fuel is quite powerful. That's why your car is loud and it has all sorts of sound dampening things to try and quiet it. A generator has a bunch of systems in place to try and make sure that reaction is safe. They have different things like vents and valves and all sorts of things that try to control that reaction, because otherwise it's just a big explosion. Actually, that's something interesting about a car engine, is it's just a series of explosions that power your car, but they're very
Hmm.
controlled and very small. Go ahead.
Are there other ways to get energy instead of those solar panel turbines, generators, and batteries? Like
Energy.
water panel, hydraulic power, and others?
Yes. So a lot of dams go across rivers, and what they can do with that is they have inside the dam is something called a turbine, which is sort of like the wind turbines there, but it's actually for water. And so as the river goes by, it spins the turbine, and much like the wind turbine, it turns that rotational energy into electrical energy. And something like the Hoover Dam, for instance, provides a lot of electricity to the area around it. Can plasma charge the robot too? Plasma's quite interesting. The short answer is no. Plasma is just another state of matter. Technically, the sun has plasma in it, and that plasma does provide energy, but you wouldn't really have plasma charging a robot directly. So if there are no more questions about power sources, I'm going to move on to control circuitry. And control circuitry is a little harder to understand because it's more abstract than maybe a motor. It's more complicated for a few reasons. The first reason is that it's just much more complex of a machine, or of an idea. If you look at, this is a pretty basic example here, but even this small little circuit board has probably 100 components on it, because each of these little black boxes and each of these little metal pads, if you look closely, you can see all these darker green lines. All of those have a very important purpose, and that purpose is usually determined by what you want the thing to do. And so that's why there's not really one great example for a controller, because it it's just so unique for each application. And yes, like I see in the chat here, this is where, if you were coding a robot, I don't know how many of you have done coding before, but if you were coding a robot, this is where the code would be kind of interpreted and stored, and your letters and numbers would be turned into electrical signals to the rest of the robot. And so the control circuitry works a lot like the human brain, and that's kind of what I've tried to show here, in that it turns thoughts and ideas into electrical signals that go kind of like your body's wiring is nerves. And so whereas a brain uses nerves to send electrical signals to your muscles, the controller uses electrical signals to send to the motors to tell them what to move, how to move, where to move, how long to move, all sorts of things. And so the control circuitry is made up of a bunch of different components. There are things that are called diodes and capacitors and switches and resistors and transistors and all sorts of different things that I could spend a whole other lecture talking about. But what you really need to know is that those create different pathways for electricity to flow through, and that's kind of what determines the logic of how the robot moves and how it acts. If you have an Arduino, then that is a controller. Yes, an Arduino is something called a microcontroller, and a microcontroller is basically just a small controller. That's what it means in the name. And so you can program it. It has built into it all these little things like you can see here. And that allows you to control motors or control lights or sensors or things that could be robots, things that don't have to be robots. And so controllers are found in things that aren't robots necessarily. Like your computer has a bunch of chips that are like this in it. Computer's not really a robot. The fan is technically motion, but that's not part of the functionality of the computer because it's not designed to move. And so your computer has a bunch of control circuitry in it, but it's not necessarily a robot. So we've talked a lot about the different parts of a robot. And so let's talk now about making a robot. But first, if there's any questions that you have that I haven't answered yet, feel free to ask them now.
Isn't potential energy about how much energy it can have? And I heard that that's what's mainly calculated in equations. I think the total amount that I can have, like, I don't remember exactly how this was described, but it was a ball at the top of a hill. It has that much potential energy, but it doesn't have the energy. I think that's what I meant. Is that?
Yeah. So it's very similar. The ball at the top of the hill is something called gravitational potential energy. And so what that means is that if the ball were to fall down the hill, it would have kinetic energy, which is the energy of motion, because it would be falling down the hill. But at the top of the hill, it's not moving, and so it doesn't have that energy. But because it's at the top of the hill, it could have that energy, and that's what the potential energy is. It's basically saying it could have that energy because of something like its position at the top of the hill, or its position in a certain environment. And electric potential energy works the same way, except instead of a hill, it's kind of an imaginary hill, where the electron is at the top of the hill and it wants to go to the bottom of the hill. And in doing so, it has to fall down the hill. But while it's at the top of the hill, it's not falling down the hill. And so it doesn't have the electric energy yet. It still has only electric potential energy. Yeah, awaiting energy. That's a good way to describe it. Is a phone in a phone is the battery source, which is in the back of the phone. In a phone, the power source is the battery. Yeah. If that's what you're asking, then yes, you're correct. The battery in a phone is quite interesting because it's rechargeable, which means that not only does energy go out of it, but you can also put energy back into it. So let's go into talking about not necessarily how to build a robot, but what would go into building a robot. And so the engineering of a robot has so many different parts to it. You need structural engineering, because what structural engineering is, it's the design, it's building it in such a way that it's strong and that it can stand up to its own weight and to its own task. For instance, if you look at a car, if your car didn't have good structural engineering, it would fall apart. And you don't want your car falling apart, especially while you're going 65 miles an hour down the freeway. And so structural engineering is really important for almost every robot. And it needs electrical engineering, and that's laying wires and motors and circuitry and all these things that make your robot move and do whatever it is you want the robot to do. And so knowing how to do that safely, do it in a way that works and that won't break is also really important. You need computer engineering. If you want to have a robot do more complex things, you want to tell it what things you want it to do. And so computer engineering is in many ways related to programming and to coding, and that it's how you tell your robot what you want it to do, how it interprets that, and how you connect your ideas of what you want the robot to do with how the robot performs those ideas. You need materials engineering. Robots are made from a lot of different materials. Oftentimes they're metal, but they can be plastic. They can be, cardboard. They can be any number of materials. And materials engineering is really important, because the material that you use has a lot of consequences for the application. So if you look at cars, for instance, there's so much engineering that goes into the material that makes up cars. And cars are designed to be strong and sturdy, but also in an accident, they're designed to crumple, because the crumpling is a form of energy transfer that actually protects the people inside of it. So if you've ever been in a car accident, or you've seen a car accident, you know that the car tends to crumple, but usually the inside and the middle part where the people are is safer than the front and back. And so being able to develop materials and metals to handle whatever sort of task you want your robot to do is really important. You also need aerospace engineering, not for every robot, but a lot of robots go out into space. Satellites and rockets, those are all robots. A few summers ago, I worked at a company called Northrop Grumman. That's a big engineering company, and I got to work on part of a satellite for something that was going to go into space. And space is a pretty harsh place for both humans and for machines. But there's a lot of differences about a machine that has to go into space, or even into airplanes, or into high altitude. And so being able to know those things, like differences in pressure, differences in temperature, those are all really crucial for building a working robot. And also, this is not an exhaustive list by any means of every sort of engineering that you need to build a robot. But last on this list, at least, is systems engineering. And systems engineering is kind of interesting, because it's not only about robot systems, but about people systems too. And so being able to coordinate a team to build a robot, that falls under systems engineering, as well as build the actual mechanical and electrical systems of the robot. So we're going to move on to the next topic. Here's a little bit more of a mathy topic. So I hope you have your math hats on, because we're going to talk about a few principles of engineering. All right, so mechanical advantage is one of the most important principles in not only robotics but all of engineering. And mechanical advantage is a very big topic, but it basically describes how you trade off input energy versus output energy. There's some complicated math here that this is something called a cross product, which you'll get to in a few years in math. But what it basically works out to is that torque, which is a rotational power, is equal to the distance times the force times the angle that you do the force at. And so let's look at this seesaw here. In this seesaw, it's set up in such a way that there's a 5-pound ball 1 foot away and a 1-pound ball 5 feet away. And as you can see, these things are balanced. And now, if you've ever been on a seesaw with somebody 5 times your weight, you know that usually it doesn't balance. And the reason why it balances is because of this principle of mechanical advantage. This ball here is 5 times as far from the what's called the fulcrum, which is the tipping point of the lever, as this ball here, which is only 1 foot away. And so they have the same torque because the angle's the same. In this case, the force that's being applied is the force of gravity, which points straight down for both of these. So the angle is the same. The distance, this is a distance of 5, and this is a distance of 1. And the force, which is based on how heavy you are, since it's the force of gravity, this is 5 times the force of that. So 5 times 1 and 1 times 5 give you the same amount of torque. And so these two things cancel each other out, and you can balance the lever. So now we're going to talk about gear ratios. Gear ratios are another form of mechanical advantage, and Gears are hugely important for a lot of robots for two reasons. Gears have two kind of primary functions. The first one is a little more straightforward, and that has to do with translating rotational motion. So if you had a motor that was spinning on this gear and you hook it up to this other gear, suddenly this gear is spinning too. And the rotational energy that came from over here is now rotating over here. And so it's a transfer of energy across the two. And so if you want to have one motor powering multiple things, one way to do that is to have gears going from the motor to different things. And though that can transfer the energy across the gears. Gear ratios are quite interesting. And the reason why these gears are different sizes is to kind of highlight that. And again, there's some math here with the rotational velocity of A over the rotational velocity of B, but you don't need to worry about the math. Basically, the ratio of the speeds, so one speed divided by the other speed, is the opposite of the ratio of how many teeth they have, assuming that the teeth are the same size and they have the same spacing across each gear. And we can use the example it gives here is 40 teeth and 20 teeth. So if you have the 40 tooth gear divided by the 20 tooth gear, 40 divided by 20 is 2. And so this speed of A over speed of B must equal 2. And so if you multiply both sides by the speed of B, you get that the speed of A has to be 2 times the speed of B. And so if these things are rotating together, for every one rotation that the big gear does, the small gear must rotate 2 times. And that makes sense, right? Because if each tooth lines up 1 to 1, and you have 40 teeth to go around here and 20 teeth to go around here, then it must be 2 to 1. But there's kind of an interesting trade-off here, and that you trade speed for torque or power. And so while this gear is moving half the speed as gear A, it's moving with double the power. And so that's kind of an interesting example of what we talked about just a moment ago with mechanical advantage, where you're trading speed for power. So let's say that there's something really heavy and you absolutely need to pull it. Gear A might not be able to pull it. Gear B could pull it, but it might take twice as long. But depending on the scenario and your usage of it, that might be what you want, or you might want it to go twice as fast, and so you'd pull it on gear A. So this is code. I think some of you earlier were talking about code. Code is, at its core, a bunch of ones and zeros. And so oftentimes you write code on a computer. And so inside a computer are millions and millions of these little tiny things called transistors. And transistors are basically switches. All they are is just on or off. And so code is a way to turn those on and off transistors into things that the human operator understands. So, if you looked at a series of ones and zeros, millions of digits long, you could never tell what it does. But looking at words like this or numbers and letters, you can interpret and tell the robot what you want it to do. And so the robot works in the same system of ones and zeros as the computer. It's called binary. And the robot in the control circuitry also has transistors. Isn't that called yes, that's binary. And binary, it comes from Latin bi, meaning two, because there are two things, right? It could be a 0 or a 1. With programming, you are able to turn your words and your variables and your functions and all these things into ones and zeros for the robot. And those ones and zeros go to the control circuitry, and it tells the control circuitry exactly where to send power, when to send power, what signals to take in, what signals to send out, and to perform all the functions that you want your robot to do. And so this is something called software. And the reason why it's called software is it's much more changeable than what's called hardware, which is the actual motors and the wiring and the sensors and all of the things that are physically there on a robot. So, we've talked a lot about math and about code. So let's move on to something that I think is pretty cool. This is competitive robotics. This is something that I've been doing since I was in third grade. So that's now 10 years ago.
Wow.
This is part of a international competition called Vex Robotics. And every year they put out a challenge. This robot actually brought to the World Championship for Vex Robotics in Kentucky last year. And so the purpose of this robot was to take these plastic balls here. You can see the yellow balls, and there were some flags that had to shoot the balls at. And so to be able to pick up the balls, which is what you see in the front here, and be able to fire them, which is what this catapult-looking thing on the right side here is. So the goal of the robot was to be able to fire these balls as quickly as possible and as accurately as possible. Lego Mindstorm is a great way to be introduced into robotics. That's how I actually started in robotics. Lego Mindstorms is a product made by Lego that it basically is an environment for making your own robots. And so it gives you motors and it gives you pieces to work with. And so there are even competitions for Mindstorms. And it's it's a good way to kind of be introduced into building robots because it gives you a lot of the foundation needed. For this robot, there's motors and there's sensors. You can see this thing here is the controller, and the battery is tucked away in here. All of these things have to be put together kind of with a purpose in mind. And so one of the hardest things to do when building a robot is that usually you're not building a robot by yourself. And for simpler robots, you can build them by yourself. But if you look at something like spaceships or airplanes, all of those things were not built by one person. And so working as a team is an important challenge, not only in competitive robotics, but in any robotics. And so being able to coordinate with your teammates about what you want to do, what you want the robot to do, how you're going to get it so that the robot goes from not being able to do anything to doing what it wants to do, to coordinate with your team, be able to communicate with your team. Those are all really valuable skills to be able to produce something as complicated as a robot. For this robot in particular, there's a lot of challenges because it had to fling these balls pretty far. And so it's not a very big lever arm to fling the balls. An interesting challenge for this robot was related to what we talked about with mechanical advantage, where because this is a shorter lever arm, you can get a lot more force out of it, but you need to put a lot of more force into it. And so we had a lot of problems where this lever arm would come up and it would bend this metal pretty much in half just because it's so powerful. And so we had to do a lot of structural reinforcements here. You can see part of what we talked about earlier with structural engineering, all these triangles. Triangles are a really strong shape. So all these triangles, you can see here is triangle, 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 triangle. All these triangles help to stabilize the robot from such powerful forces because that's what we needed it to do. So that if you didn't think that this was cool, you'll probably find the next thing cool. This is something called BattleBots. This is a show that's on TV. It highlights some very complicated robots that basically are designed to destroy each other. And they do so in a number of ways. You can see this one on the left has a hammer, and these ones have big spinning discs. But this is a show that, well, it is TV, so it's kind of sensationalist and based on emotional response more than engineering, but there are some very, very high level engineering decisions that are made with these battle bots. I've never worked on one personally, but I am friends with a few people who have, and the amount of engineering and building and constructing and programming and designing and teamwork and all these things that go into the robots are insanely complicated. And if you're interested in engineering, I'd recommend watching the show. Even if you're not, I'd recommend watching the show because it's a great show. But it shows off different engineering strategies and building and how to make a robot do what you want it to do. So this is kind of one example of some very high level robots. Another that you might have seen is there's an organization called Boston Dynamics. Boston Dynamics makes really incredibly cool robots. You can see this one on the right is doing backflips and jumping up and down, and that's a full human-sized robot that has no wires connecting it to anything else. It's all been built and programmed by someone using these processes to do exactly that. And at the very core, it's all motors, it's all power sources, and it's all control circuitry. And all of these robots have that. Robots are all throughout the world today, in basically every field. If you want to be a doctor, there are medical robots. This over here on the right, it's a very recent development called the Da Vinci machine that allows doctors to do very complex surgeries, even when they're in a different country than the patient, because the machine on the left can communicate with the machine on the right. The picture on the left here, this is a robot in a factory. The robots in factories can be incredibly complex, so they can be incredibly simple, but almost every factory or every production facility has some sort of robot in it, and that's just because robots don't need to be they don't need to eat and sleep like humans. Why don't they use robots in wars? They do use robots in wars. Boston Dynamics actually has worked with the military to develop robots that
Be used in
carry
war?
supplies. Absolutely. So I mean, even a really basic example, think of it this way. Planes and tanks and all those things and ships, those are all robots. So to get back to what we were talking about earlier, and some of you brought up, was the possibility of robots harming people. I know, I guess war is an example of that. Yeah, there are many dangers that can come with robots. That brings
Also,
to something called Asimov's 3 laws of robotics. Asimov was a theorist who even long before modern robotics came up with kind of guiding principles for how robots should act. And those are not usually directly implemented, but the ideas behind them are implemented in most robots today in order to make sure that they're safe. If you look at self-driving cars, because self-driving cars is a technology that it is starting to emerge, it's kind of on the horizon. Self-driving cars, for the most part, are still dealing not as much with the technology of driving as much as the decision making. So, for instance, if there's the classic problem of if there's a person walking in the crosswalk and the car can't slow down in time, is it going to swerve? How do you calculate the value of a life? What decisions do you make? The decision just has to be made, and that's where a lot of issues of morality and of machine judgment come in. There's kind of a very high level theory of something called singularity, and singularity is basically the point where robots become better than humans at making robots. And that's kind of weird to think about, but at some point, there will be a robot that designs a better robot. Can a robot make robots? Yes and no. So yes, robots can make certain types of robots. Usually robots that are more simple than themselves. And where robots start making robots that are more complex than themselves, that's where you get the sort of singularity. But there's something that's very interesting called a von Neumann machine. Is basically a fancy word for a machine that can make copies of itself. Humans are technically von Neumann machines, right? Humans make other humans. And so when you have robots making other robots that are as good as themselves or better, that's where you start to get into some of those issues of singularity and all these movies you see of robot uprisings and robots taking over the world. But so that's basically the end of what I have to say. Thank you for listening to what I have to say. I hope that I've inspired you about learning about robotics and even if you're not interested in building robots, well, thank you. You've been a great audience, and good luck with robot building or whatever else it is that you want to do.